So
I'm always waiting for that text message in the morning.
Yeah.
So it's canceled today.
you're like, you kind of get trained for it, yeah. And today was maybe a little iffy.
Yeah.
That's the first thing I did this morning.
Did too. So, alas. So I'm thinking we'll knock out 10, which is 40 slides, and there's a good chance we're going to start 11. You're like, how could you? But you'll see what I mean, because a lot of this stuff we've covered before. And I don't mean to confuse you from Chem 1, because you got it from Chem 1. We just need to add 2 ways to express how concentrated the solution is in Chem 2. We need to build on that. So these are like things you kind of already know. A solution is a mixture, specifically a homogeneous mixture. It doesn't have to be a liquid mixture. It could be, solid, gas. Okay. And we generally talk about, there's too many S's. We talk about the thing that you're in lesser amount is your solute, and the thing that you're dipping it into is the solvent. Solute plus solvent is equal to solution. Now you could have more than one solute and a single solvent. And we said if water is your solvent, then it's an aqueous solution. All right. So some of this is going to be like, yeah, we already talked about that, but we're going to add, like I said, we're going to add to it. Most cases we talk about, in terms of concentration, we talk about amount of solute per a given amount of solution. Okay, like molarity, moles of solute per liter of solution. Okay, weight percent, mass percent of solute or mass of solute per mass of solution. Okay, that one with the asterisk down there, and this is our new one we're going to introduce today, is talking about terms of concentration solution, amount of solute per given amount of solvent. This is new. Okay. So, new. This is old. This is new. And the difference is we have a relative amount of solute in both cases, but instead of solute, but relative to solution, it's relative to the solvent. That's it. Okay. Some general terms when we're talking about the concentration of a solution. If you say it's dilute or if you say it's concentrated, that means you have a lot of solute per given amount of solution or solvent. If it's dilute, that means you have a small amount of solvent per given amount of, a small amount of solute per given amount of solution or solvent. Dilute and concentrated, you kind of know that. So these things I feel like we've covered before. Mass fraction. Remember the difference between mass fraction and mass percent is a factor of 100. Case of mass fraction, it's solute per 1 gram of mixture. In the case of mass percent, it's solute per 100 grams of mixture. Mole fraction, I'll kind of remind you what that looks like. I'm not sure if we talked, I feel like we did, but we'll talk about that again. I don't do much with volume fraction, but in all of these fractions, it's a relative, again, it's solute per given amount of the mixture, the solution. Grams per liter, that would be kind of going to this one. Grams of solute per liter of solution, molarity, that's not molarity, but molarity, capital M. This is the new one, molality. One of my pet peeves, when I'm learning things, I'm all about like the letter sets me off. I'm like, oh, I remember that. And in this case, we have 2 very similar words, and we have the same variable, but it's case sensitive. And actually, they do that in astronomy with regard to how bright a star is. They have a bare brightness and absolute brightness. But molality, I'll go ahead and tell you, is this one right here. So molality, the lowercase m, is going to be amount of solute, and it's going to be moles of solute per actually amount of solvent per kilograms of solvent. Just kind of get you used to the idea. That's it. So then in my notes, I kind of take off and I kind of remind you a little bit of a few of these and then introduce molality and then do some problems. But, oh yeah, then I also talk about parts per million and that sort of thing. So anytime you have volume, whether you have volume is like an amount of solution, it doesn't have to be, but if you have volume of solution, then that actually depends upon temperature. This one is temperature independent, and that's kind of why. Well, that's one advantage of molality. I feel like I'm being kind of a jerk about it. Molality instead of molarity. Molality is an advantage. It does not depend upon temperature. All right, mass fraction. By definition, what does that mean? If you have the mass fraction of a component in a mixture, you have, or to calculate it, you would take the grams of the component divided by the total grams of the mixture. That would be the mass fraction. Mass percent, we're used to more, and we can scale this up and just multiply by 100%. So that's why mass fraction and mass percent are totally related by a factor of 100. So there in the denominator, this is saying if I had something, so I have my solute is A, and I might have multiple solutes. Let's say I have A, B, C, and D. Let's say I have 4 solutes, okay? And then I'll make E my solvent. Okay, so what I would do is take up the total mass of that, all 5 of those things, put it at the bottom, and that would give you the mass fraction of A. What else we got? Mass percent, like I said. All you got to do is calculate mass fraction. What is mass fraction? It's the relative mass of the component to the mass of the total mixture. In this case, we're kind of using a type of mixture as a solution, or a solution as a type of mixture. Mass fraction is unitless, and mass percents, we use the percent sign. So in working in Gen Chem 1 and actually Gen Chem 2 and working science problems, I'm all about unpacking things. So if somebody tells you, the unitless number, you're looking at 0.159 a mass fraction, you need to know what that means to use it in a problem. You're unpacking it. So that means you have 0.159 grams of that component in 1 gram of the mixture solution. Mass percent, slap on a percent sign. The grams we say the grams cancel, grams of component, grams of mixture. But if we were given, again, a percent, I should never see strung up in working your problems anywhere, 15.9% as a term to work the problem. It should be unpacked. What does that mean? Well, in this case, the solute is sucrose. So that means in 100 grams of the solution, I would have 15.9 grams of sucrose. So one of the themes about, I think all physical science, including physics and chemistry, is let your units do the heavy lifting. Make sure your units are what you want them to be and see what units you have to deal with to get from where you are to where you want to be. Let the units do the heavy lifting. So dilute solutions have a small amount of solute and a large amount of solvent. A very common, especially in environmental samples, is the term parts per million. Parts per million. Million is 10 to the 6th. Okay. Oops. So let's kind of look at what parts per million mean. Actually, that's ppm, parts per million. And what is ppb? Parts per billion, yeah. 10 to the 9th, exactly. So if someone says, I've got an environmental sample here, and you're looking at so many parts per million, what that means is that that would be the number of, let's do it this way. Let's see. Say something is running 15 parts per million. Unpack it. That means you have 15 grams of the component in 1 times 10 to the 6th grams of the, I'll put A, solution. Okay? Another thing is million needs 10 to the 6th. So if you have the mass fraction of something, that's parts in 1, then you can scale it up to parts per million if you multiply it by 10 to the 6th. That's kind of weird. That is true. Parts per million. Here's one for you. Oof. This only works for, here's my jug, and I have 1 liter, exactly 1 liter of H2O. And I'm gonna just kind of put a solute in it, just barely put a solute in it. So here's the deal. Let's see if I can convince you of this. All right, we got time. What is the density of water? 0.98. Very good. Round to 3 sig figs. Actually, I think at 4 degrees I usually go with 1.00. But I'm not going to argue about that. 1.00, and units be grams per milliliter. Cool. So, how many milliliters in a liter? Yeah. So, in this jug, what if I take 1,000 milliliters times 1 gram per milliliter? What do you think? I'm liking 1,000 grams. Okay, good. Right. So, now here's another one. In order to have this make sense, how many milligrams are there in 1 gram? I know, this almost feels like my math is usually a lot more straightforward than this. But do you guys buy this, that if I have 1 milligram in, this is component A, in 1,000 grams of solution, because you figure the mass of those little, there's not much there, so it didn't really add to that mass. That's kind of the point of a dilute aqueous solution. Do you guys buy this, that, what is this? Yeah, this will work. If I were to go ahead and, I don't know how you want to do this, but there's a factor of 10 to the 6th there. Can you see the factor of 10 to the 6th there? I guess to kind of finish that thought, I would go ahead and convert this to 0.001 grams over 1,000 grams. That would be component A to solution. Now, do you see it?
Oh, I think so.
I do. So now they're both in units of grams. Okay. Let's see, how could we go ahead and we can finish that thought. What happens on our calculators if we take 0.001 divided by 1,000? So it's 10 to the negative third. You get 10 to the negative 6. 10 to the negative 6th, and that would be grams of component A per grams of solution. Okay. I don't usually do this little proof. I usually do it like this, but my point is, if it's a dilute solution and the solvent is water, dilute aqueous solution, then actually the way this works is 1 part per million of the component of A is approximately equal to 1 milligram of that component per 1 liter of the basically water that's floating around. But that only works. The more you go ahead and increase the mass of this, the more that this becomes not true. The mass of your solution is no longer 1,000 grams, it's something else. Okay, so anyway. So parts per million and milligrams per liter are the same thing. So that might come in handy sometime. So parts per million is essentially equal to milligrams of A per liter of solution, milligrams per liter. All right. Mole fraction, I think you'll probably do okay with this one. I feel like, did we do mole fraction before? It's got the X thing going for it. With partial pressures, we did partial pressures, didn't we? Dalton's law of partial pressures in Chem 1? No? Is that a Chem 2 thing? Use the mole fraction to calculate the partial pressure or something? I feel like we did.
Yeah, we did. Yes.
Yeah, if you have a gas mixture and you want to know the pressure of a component, good. If you want to know the partial pressure of one of the elements, one of the gases, you can take its mole fraction times the total pressure to get the partial pressure. Okay, so this is a similar thing. This will have a similar thing to you. If you want to know the mole fraction of anything, kind of do like what we did before. You look at your thing in total. You have to knock out the moles of your component of interest, and you have to knock out the individual moles if you have more than 2 components. You put the moles, total moles in the bottom, the moles and component of interest in the top. Yeah, very good. Okay, yep, so mole fraction is the symbol X, and we use a little subscript to say mole fraction of what? Mole percent, then, is mole fraction times 100. All right. Grams per liter, I think we're okay with that. Grams of solute per liter of solution. Doesn't have to be an aqueous solution, doesn't have to be dilute. Okay. And what we do to knock out grams per liter is to take a volume solution, grab the mass of the component of interest and divide by the total volume. That's it. Mass and units will be G/ml or G/L, grams per liter. So now I have a couple examples, and I feel like we did this in example in Chem 1. The solute we're working with is sucrose, and I'm not even going to draw a picture because, well, I guess I could. But I'm sure you're fine with this. The reason I'm drawing a picture is with all solution concentration problems like this, I draw a picture. So it says that we are going to dissolve 32.3 grams of sucrose. And if you're working the problem, you can use the formula or use an abbreviated name as long as you're consistent, kind of show what you're doing. And we're going to dissolve it in 225 milliliters of water. So if you're like, don't make it harder than it is, right? Our target is question mark, we're after grams per liter. Not too bad. I'm just going to take this number, divide it by that number. Totally. So here we go. I feel like this is exactly the one we did before. Take the mass divided by the volume. Of course, we got to fix the volume part because I want grams per liter, not grams per milliliter. So I can introduce a term. The second term would be 1,000 milliliters over 1 liter. And that should do it for me. And then I round it to 3 sig figs. And that should be good. So I probably would write it this way down here. But 124 G/L, grams per liter of sucrose. And again, if I'm using SUCC for sucrose, I could write SUCC for sucrose. The formula for sucrose, the molecule has 12 carbons, 11 hydrogens, 12 carbons, 22 hydrogens, and 11 oxygens. So, in the problems that are going to be assigned for this part, I mean, you guys have a lot of homework due Monday, don't you? Oh, Lord. Better you than me. Because we've still got some topics to cover before your test on Thursday. But we're going to piggyback on this. What I started to say is it's common to take one solution and knock out how you express its concentration in different units. So we're going to do that with this one. Then, and we're going to piggyback from our 144 grams per liter. Okay, so molarity, Gen Chem 1 thing, molarity is moles of solute, in this case sucrose, going to be sucrose per liter of solution. Okay, so, and this is just to try to remind you that it's not written like I'd want it, but if you have to use 3.0 M, big M, now remember there's a little m, this is a big M, I want you to know that that means 3.0 moles, in this case, of HCl, because it's a molarity HCl, per 1 liter of solution. Okay, so we need to be able to unpack that. And, you know, the reason you unpack it is because sometimes you'll use it just like that, and sometimes you'll flip it, depending upon how your terms are setting up in your problem. All right, so we're going to piggyback from that 144. So before we had 144 grams of sucrose per 1 liter of solution. How do we get from grams to moles? Gen Chem 1 thing. Molar mass. I can tell it's hurting your brains. You need to get the molar mass of sucrose. And this is where we needed to know the formula. Couldn't just call it SUCC. So we're going to take 12 times the decimal number for carbon, 12.01, plus 22 times 1.008 for hydrogen, plus 11 times 16.00 for oxygen. And it seems like just the other day we were talking about molar masses. So this is the MM, this is the molar mass of sucrose. If I were to be kind of unpack that, remember what that means is 342.30 grams per 1 mole. So let's go ahead and again, we're going to not reinvent the wheel. We're going to pick up with 144 grams per liter. So if we make that our first term, how can we use molar mass to get to moles per liter? Yep, one mole on top, the 342.30 on the bottom. You got it. Exactly. And again, this is where I kind of alluded to, if you have defined C11H22O11 as something easier to write somewhere in your problem, that's a good thing. And I think also, I think about kind of how you communicate. If you're only dealing with one solute, you probably don't have to write out what the solute is. I think that's legitimate. If you have more than one solute, like a stoichiometry problem, then you got it. Okay, 3 sig figs. So you're looking at the value around the 3 sig figs is 0.419. And then the units explicitly would be moles of sucrose per liter of solution. But as you know, we're used to kind of doing this, the 0.419 capital M C12H22O11. So either one of those are great. All right. Molality, little m. Okay. So, I mean, really, you couldn't come up with another variable? It's just so grr. So molality is moles of solute per kilogram of solvent. I know it feels weird, but the fact that now we have removed the volume from it versus molarity, that means this does not depend upon temperature. And that's actually probably one of the reasons it's so helpful. But here's one for you, and don't dwell on this too much, and I'm not going to pull you through a proof, although I've proved it to myself before. If your solution is dilute aqueous, so if your solvent is water and there's not much solute in there, well, actually we can do then that means that the mass of a liter is, what's 1,000 grams? 1 kilogram. Okay, so if basically the mass of your solute is negligible, then your molarity you got is equal to molality.
Just for water.
Just for water, exactly. Just for the solvent water, and it's got to be pretty dilute. Yep. Don't count on it, I don't think. I'm trying to think about problems that you'll be working. All right. Yep. So since the volume is kind of, will change with temperature, like I've been saying, that means molarity is subject to getting different molarities at different temperatures. And molality, since we don't have a volume in that ratio, it's moles of solute to mass of solvent, then it's independent of temperature. So here's one for you. In both of these cases, they have set aside 0.1 mole of potassium chromate. Okay. So in one case, is this right? Yeah. In this case, this is 1 molar. So what they did was what we're used to doing. They took the solid, they took the 19.4 grams in there, and they diluted it with water, made sure it mixed and everything. Removed the stir bar, and then put it up to the line. And I don't know if you can see it right here, but there's the line up there. So this is a volumetric flask. It has a capacity of 1 liter. So 0.1 moles of K2CrO4 brought up to volume to to a final solution volume of 1.00 liters gave you 0.1 mole. This one is 0.1 molal. The right one is 0.1 molar. The left one is 0.1 molal. So how do you get molal? How do you get 0.1 molal? Well, again, you're dealing with 0.1 moles of the solute, so you'll have your 19.4 grams. But in this case, instead of making your overall solution 1 liter, you have to dump in 1 kilogram of solvent, which is water. So you're dumping in 1 kilogram of water. You're not looking at the little line there because it's molality. You're going with mass of water. That's why it's weird. It's like volumetric flasks don't work with preparing something a certain molal. Mass of water. Mass is independent of temperature. So do you see, does this make sense then? That's why this is going to be, actually you guys will have problems where, I'm thinking of it right, where you will come up with molal, you'll see which one's more concentrated. But to me, doesn't this look a little more dilute? So this would be less than 0.1 mole or, so more dilute.
Right, so what you're saying is like on the right side, the overall solution is 1 liter, right?
Right.
And on the left side, that's like 1 liter of water plus whatever you have.
On the, wait, let's see left and right. So this one was, say that again.
So, okay. So the right one is like the overall solution is 1 liter.
Right.
But then on the left, they have like 1 liter of water plus whatever they're adding.
Yeah. Depending, well, now I hesitate. 1 liter is not necessarily, it's got to be more accurately 1 kilogram. Because the problem with water is the volume will change with temperature.
And then you're adding the other stuff.
Yeah. And then you have the 19.4 grams of solute. Yeah. So, yeah. Well, that makes sense. But we've done colorimetry where with the little cells, you look at absorbance, right? Okay. With your nickel 2 chloride, I think it was. So my thing about this is, if we were to put those in there, this would be a little more yellow. This would be a little less yellow, right? And it's like got the same mass of like the 19.4 grams in it, but this actually has more water. But another way, this actually occupied some of the volume as you added some of the water. And the combined volume was 1 liter. They're kind of two different things. You would not use a vol flask to come up with if you're preparing a solution that was, you wouldn't use any volumetric thing if you were preparing moles to kilogram of solvent. All right, so we're going to work this problem 2 different ways. And I didn't look at my notes real good, so we'll see how this goes. But I mentioned drawing, so you don't have to, but if you don't do a drawing, what I would do is pull out those numbers and at least put them on the piece of paper as you're working the problem, either for homework or on a test. They are like your puzzle pieces to get down the road. So this is a classic where you're given some information and you're asked to say how concentrated, in this case, the HNO3 is. That's the solute in your solution. I will tell you that for this sort of problem, we aren't going to use, I think that's right, we aren't going to use the temperature, but the temperature is just important to kind of get a sense for, to kind of set the stage. So our solute is HNO3. If I were to unpack 70, and I think I'm going to do this on the next slide, but I'll do it here too, 70.0% HNO3, what that means is there are, in 100 grams of solution, 70.0 grams of HNO3. Wow, that's pretty concentrated. The density, I'm going to jot that down. But remember what density units mean? Grams per mil, grams of what? And this, they're always going to be grams of the whole solution. Sometimes students are confused by this. So when I put 1.42 grams per 1 milliliter, I need to go ahead and say grams of what? And it's the grams of the whole mixture. You can't get the density of just the HNO3. That'd be silly. So, question mark. We're supposed to knock out a few things. Molarity, and molarity units are moles of HNO3 per liter of solution. We are also supposed to knock out molality, moles of HNO3 per kilogram of solvent. In this case, it's an aqueous solution, so that'd be kilogram of H2O. And we're supposed to knock out mole fraction. And that's going to be the moles of HNO3 divided by, there's only 2 things in here. Here's my HNO3 and the rest is water. So the thing in the bottom is going to be moles of HNO3 plus moles of H2O. And you get a cup of coffee and you come back. Okay, so this is what we're after. These are our puzzle pieces. Now, the 2 ways we're going to work it depends upon, we've done this before. I know we've done this. Like if you're trying to work a weight percent problem, you say based on 100 grams of the stuff, then I can go ahead and turn those weight percents into grams. So we're gonna choose our own basis. Okay. So hold that thought. Let's go ahead and knock these out. In order to work this problem in the margins somewhere, you're going to want to know the molar mass of nitric acid, HNO3, and the molar mass of H2O, which is committed to memory. And students might be like, well, how would I know to do that? Well, to me, looking at what we're after, I'm going to need to know relative moles. Okay? So here's the basis part. The first basis we're going to work it is, and sometimes I'll say assume, or what our basis is. So I'm going to say assume we have 100.0 grams of solution. That's my basis. I can do that. It's not cheating. And then let's see how the chips kind of fall into place. So this slide right away says, well, if I have 100 grams of solution, then I know that, yeah, I have 70.0 grams of HNO3, and the other component must be my 30.0 grams of H2O. And can you already kind of see where that's going to help us get down the road? I can go ahead and turn those into moles, and I can knock out this relative mole fraction. Let's see. So actually all of these kind of fall into place. Let's see how that works. Well, I can get to the volume of the solution. If I know my basis is 100 grams of solution, I can go ahead and use my density. So how do I use my density to get to a volume of solution? Yep, grams on the bottom and milliliters on top. Very good. Then how do I get it to liters?
1,000 ml.
Wow, 1 liter over 1,000 milliliters. Oops, sorry. Oops, I guess I'm not doing that, but I could. Make sure we're on the page. I didn't do that here. But it would be 1 liter over 1,000 milliliters. But if we leave it in milliliters, which I'm sure there's a reason for that, I can't remember. Are we good with this? On our base, based upon our 100 gram base solution, we're looking at 70.4 milliliters of solution. We can get to moles of HNO3 just using that mass, that 70 grams, and then using the molar mass, the flipped version of the molar mass a few slides ago. So that's be 70.0 grams of HNO3 times 1 mole of HNO3 divided by 63.02 grams of HNO3. Round to 3 sig figs, you're looking at 1.11 moles of HNO3. Very common in working these problems where you have a set of different ways of describing solution concentration from the one problem is that we're going to use that number a few places. At 1.11 moles. Okay, so moles of H2O look like this. We'll take the remaining 30.0 grams of H2O, multiply it by 1 mole of H2O over 18.02 grams of H2O, 3 sig figs, that gives us 1.66 moles of H2O. And you know, when I'm grading these problems from y'all, it's kind of, I look at how you did it, but I kind of just look at the answer because there's so many different ways to work this, it feels like. They're all very similar. One thing about it is if you have a heading like this, moles of H2O, to me, you have set the stage, you don't have to put H2O in these. What you're after for that step. All right, let's see what we do next. Well, we got some options. Knocking out molarity, we're going to take that moles, that 1.11 moles of HNO3, divide it by 70.4 milliliters, and we got to go ahead and fix the milliliters to liters, which I could have done that before, but no. 3 sig figs, you're looking at a molarity of 15.8. And again, on my solutions, you might see me at this point just, again, in a hurry. And it's no worries. I would go 15.8 big N HNO3. Same thing. They're kind of exciting because then you're like, that's 1. And that's molarity. Molality is going to be similar, but here I'm going to have to put the mass of H2O into the volume solution. So what do we have, like 30.0 grams, okay? So here we go. Molality, we're going to put the moles of HNO3 in our, based on our basis here, 1.11 moles of HNO3, 30.0 grams of H2O. Now, molality is moles per kilogram. So how can we go ahead and get it, the denominator in kilograms?
1,000 grams.
1,000 grams of H2O over 1 kilogram of H2O. Yep, our grams of H2O cancel, and we have units of moles of HNO3 per kilogram of solvent. H2O, yay! 3 sig figs. That is our molality. And again, I just get so excited at the end. Sometimes you'll see my answer key, I'll just put 37.0 little m HNO3, molality, 37.0. And then the last but not least, mole fraction. We can do that. We can do that. So mole fraction, it'd be the moles of component, which is HNO3, divided by the total moles. So 1.11 moles of HNO3 divided by quantity 1.11 plus 1.66 moles in your solution. Round to 3 sig figs, and you're looking at a mole fraction of 0.401. And I probably would do the mole fraction HNO3 is equal to 0.401. And it's usually unitless. All right. So here's the other, and I like this one. I don't know why we need another one, but we're going to do another one. And it kind of depends. Remember, this was our original information given. This is all we were given. And we decided to go with 1.00 grams or 100 grams, 100.0 grams of solution because of this. What if we did this? What if we said, assume you have 1.00 liter of solution? And the reason we would do that is to take advantage of this. Okay, and so let's see how things kind of fall into place. Well, we can use the density of the volume of the solution and the density of the solution to get the mass of the solution. It would look like this. We have 1.00 liters. We'll use our non-flipped version of density, 1.42 grams solution over 1 milliliter solution. I can't remember if I take it to kilograms there. Yeah, I do. Oh. Oh, I see. Notice I was like, oh, you can't do that. The first and second terms are units of liters and milliliters don't cancel. So I went ahead, you can put them in any order you want to. But then finally the third term is I put the 1,000 liters over 1 liter. And everything cancels except for grams of solution. And do we go to kilograms or do we leave it there? Okay. So you're looking at 3 sig figs only, so 1,420 grams of solution. So here's where, do you see now we can use the weight percent to go from grams of solution to grams of HNO3. So it looks like this. Our first term is that 1,420 grams of solution, and then we just plug in the weight percent of HNO3. 70.0 grams of HNO3 per 100 grams of solution. Your units of grams of solution cancel. We're left with grams of H2O. I'm sorry, for units of grams of HNO3. Round to 3 sig figs, you're looking at 994 grams of HNO3. So how can we get to grams of H2O? Nope. Nope. Look at the solution. It's only got 2 things in it.
Oh,
Yeah.
You can just take off the mass of HNO3.
Yeah, your 1420 just has HNO3 and water. So you have to take your 1420 and subtract it. So here we go, mass of H2O. Oh, well, I guess that's one way we could do it. Look, my bad. I'm going to go back and use the weight percent of water. I could have done that, but using the 3% of water, it was 70 HNO3%, 30% H2O. So, sorry about that. Could have done it that way. So you're looking at 426 grams of H2O. Now, granted, this approach doesn't seem like you're getting close to answering your questions. It does, but it doesn't. Okay, we can use the molar masses now to get to, yeah, we're doing pretty good. Let's see how we use these. The moles of HNO3 in 1 liter of solution, we can take that mass of HNO3, 994 grams, use the molar mass of HNO3, 1 mole over 63.02 grams, and 3 sig figs, that will give us 15.8 moles of HNO3. These are just kind of pieces we're going to assemble to get our concentrations. Moles of H2O, we're going to take that 426 grams of H2O, multiply it by 1 mole over 18.02 grams. Round to 3 sig figs again, you're looking at 23.6 moles of H2O. Now we should be getting different numbers here because it's a different basis. I'm telling you, when we go to do all our last divisions, it's going to give us the same numbers as the 100 gram solution basis. These are just kind of things in the margin we can assemble. I can kind of see how it's going to come together. And the more you do, the more you'll be like, oh yeah, I know what to do here. It's like anything else. All right. So we have some pieces we can use. Molarity is moles of HNO3 per liter of solution. And the volume of solution was 1 liter because that was our basis. I can do that division. 3 sig figs, you're looking at 15.8 molar, capital M, HNO3. Let's do another one. Molality, shall we? Oops, sorry. All right, molality would be that 15.8 moles of HNO3 again, divided by, we're on our way to get per kilogram of solvent. Well, we know we have 426 grams of H2O, that's our solvent. And like we did before, if we introduce a term, 1,000 grams of H2O over 1 kilogram of H2O, then we get moles of HNO3 per kilogram of H2O. 3 sig figs, and so you're looking at 37.1 little m molal, 37.1 molal HNO3. Number sounding familiar? And then last but not least, mole fraction. In the numerator, we're going to put the 15.8 moles of HNO3, and in the denominator, we're going to put 15.8 plus 23.6. So that would be the moles of HNO3 and the moles of H2O as we set up the problem. 3 sig figs, and you're looking at a mole fraction of HNO3 is equal to 0.401. Again, mole fractions are usually unitless. Well, so much for starting the next part. So, it is what it is. Yeah. So, we're going to have a crazy Monday, Wednesday next week.